Hi there, this is part 4 of linear independence and spanning sets. This is part of the curriculum, one of the lectures for linear algebra math 2010. So wrapping up the previous example, the example previously discussed, we want to refer to this definition, which states that we are given a vector space V. We're going to consider a subset of that vector space that has the property that the span of that subset equals the entire space. We're going to consider that as a spanning set. That's what we're going to call that subset, a spanning set for the vector space. And so as an illustration of this, we were working with this set W defined in P sub 4, and more specifically, let's see, we were working with a set S, a subset of W, okay? And so the point being that that set S that only had 4 elements was a subset of W, and we wanted to show that this was a spanning set, okay? So the argument at the end was that if we were in the process of showing that any arbitrary element of W, which has this form, a fourth polynomial with degree 4, if that arbitrary element can also be expressed as a linear combination of those elements in S, of those members of S, then that's the point at which I want to illustrate something, okay? So in this part of this proof, we were then able to find values for alpha, right? So this, for each alpha, this would be the value. This here is alpha 1, and this is the value for alpha 2, and this is for alpha 3, and there is for alpha 4. So it is possible, even when A, B, C, D, and E are constants, it's possible to find values of alpha for which we can represent that arbitrary element as a linear combination of those. So these, by finding these values of alpha, we are showing that R, that would be R of X, is in the span of S. And since R is something that was an arbitrary element of W, this is for any given element of W, you find that that given element of W is also an element of S, then that implies that W is contained on the span of S, okay? And this gives that part of the relationship we wanted to show, which gives us this part. We had already established the first one, that the span is contained in W, and because we have both, then we conclude, that's the final conclusion of that part. So I just wanted to emphasize that those little details of that previous example before moving on to the next examples, where see, this example is something that has to do with the set, with a spanning set on the vector space of matrices. These are matrices that have 2 rows and 2 columns, and this considers a set Z of 2 by 2 matrices, for which there are certain relations between the entries of this matrix. Okay, so here this matrix has 4 entries. Here expressed as first column AC, second column BD, or first row AB and second row CD. And those entries of the matrix satisfy 2 equations. Notice these equations are set equal to 0. So these are 2 linear equations. This is a system of linear equations. Okay, and what we want is to find a spanning set for this set Z. So let's see how this works. Okay, so we need to construct a limited number of matrices in C such that every matrix in there can be expressed as a linear combination, right? So suppose we're working with an arbitrary matrix in this set, And what we want to say about this arbitrary matrix is that if we pack or store the entries of this matrix, there are 4 of them, we store them as a vector, then we should note, maybe let me write something before I say more. So the conditions that define this set are 2 equations involving the matrix entries. And so these equations are considered a system, homogeneous system with linear equations. So in matrix vector notation, this would be the coefficient matrix. Look at the first equation. This defines the coefficients in the first row of this matrix is 1, 3, -1, -5. And we're thinking here as A, B, C, and D as the variables on this homogeneous system of equations. So thinking in terms of homogeneous systems, we could then refer to the null space of this matrix of coefficients, okay, which is what we say next. So being an element, being a member of this set Z, is equivalent to say that the vector defined by the entries of that arbitrary member, that vector is a member of the null space of this matrix. Okay, so we're going to use that next. So what we know about null spaces is that we can take that matrix of coefficients, right? And take that matrix of coefficients, row reduce it, in order to write the null space of this matrix. Okay, so this will be convenient. So because in this case this matrix row reduces to this, then we have that any element of the null space of the original matrix would also be an element of the null space of the RREF of that matrix. Okay, so we can express, we can use this to express the set Z. Okay, so let's review this. So Z is made of matrices that satisfy these 2 equations, but because of that RREF calculation, because of that observation, those entries defined in a vector for which these equations are satisfied are also entries that would satisfy the equations involving the RREF of the previous dimension matrix. Okay, so it is fair game to write the set Z in terms of the equations for the homogeneous system that we obtain from the RREF. Right, this is what we had in the previous slide. And so by doing that we notice that we can write A in terms of B and D. So this is exactly what the treatment of dependent variables are, right? So because the RREF is defined in this way, so here you would say that the set D contains 1 and 3, okay, and so this is going to be associated with 1, this is going to be associated with 3, so A and C are dependent variables, and so F here would contain 2 and 4, right? So those are the free variables. So therefore we could write A in terms of B and D, and we can write C in terms of B and D, and so on, right? So this is that idea of thinking in terms of dependent free variables. So here we rewrite these expressions in terms of as dependent variables in terms of free variables, right? So here is A in terms of B and D, and here is C in terms of B and D, but I mean what happens is that you have that plus 0B. Okay, so what we do next is that we go into the entries of the matrix and replace A and C. Okay, so A is minus 3B plus D, so here's that expression for A, and then C is minus 4D, and now we write that B and D are any given values in the complex plane. Okay, and so what we do next is that we can write that matrix as the sum of two matrices, and indeed this allows us to write this as the sum of two matrices, and the first matrix only involves the letter B, right, one of the free variables, and this one only involves the other free variable. Okay, so we can write that as a linear combination where each part of the linear combination is a scalar multiple. So this is a scalar multiple B of this matrix, and this one is a scalar multiple D of this other matrix. Okay, so by doing this, now we can say that Z really is a set made of linear combinations, because this is nothing other than the span of the set containing this matrix. Now you can think of this as, I don't know, some W1, this could be some W2, right? So this looks like the span of a set that contains W1, W2. So these two matrices are a big deal because they are the matrices that span, that those are the members of the span. So this tells us that this set containing those matrices spans Z. In other words, we would say that the span of this set, the span of Q, is exactly equal to Z. Thank you very much.